Okay, I think it's almost at 10. Maybe we can start early, right? Because maybe some of you will have some prayer. So once again, we will welcome Dr. Hakim. Please, Pak Hakim.
Thank you. So what time should I stop, Evan? Around 11 or something like that?
Well, yeah, then we can have some discussion, right?
So do we have some participants from the eastern part of Indonesia? So they might have a Friday prayer earlier than us. But it should be okay, I think, because the time window is time window. I'm borrowing the time series. So the time windows is up to 11:15, and I still have the 30 slides. So the time resolution must be very short, very high. So yes. I try to do it efficiently so that when you do time series analysis on my talk, the power spectra is still high. Okay, so let's move on to frequency domain analysis. Just to remind you that we just finished the time domain analysis. And actually, PDM is not the only recipe for time domain analysis. There exists what's so-called the string length method, but I'm not going to touch upon this. That's a very old technique. It was introduced by Dvoretsky in 1973, but I think you can easily find it in the journal and try to figure out what is the difference between the link strength and line strength method and the phase dispersion. But phase dispersion minimization is most popular technique that has been used by astronomers to make time series analysis, especially for variable star and spectroscopy. Now, bulk of the papers in time series analysis falls into this frequency domain analysis. There is a reason, because this field is quite mature in signal processing. It has been used well by electric engineering group from time to time, but under a very different criteria of data. So we basically adapted this because it's quite mature. And then what astronomers do for frequency domain analysis is actually try to improve and to adapt this frequency domain analysis into specific requirement in astronomical observation. So let me go through this. Okay, I will, because my time resolution must be very high. Yeah, in Fourier analysis, the basic is to fit a series of sine curves. So, and actually before we went to the brick, I gave you an illustration of how sine curve is fit into the data. So Fourier analysis attempt to fit this with different periods, but instead in the time domain, Fourier analysis firstly try to transform all this time domain into frequency domain, because it turns out to be historically doing arithmetic in the frequency analysis is much easier, arithmetic operation, rather than in the time domain. Remember the concept of convolution, theorem of convolution. Once you transform to function into the frequency domain, so the convolution is basically the linear multiplication in the frequency domain, but not in the time domain, not in the real domain. So that's why to ease analysis in the time series, so Fourier analysis require us to bring all the data into the frequency domain. But then many things that must be be cautious, especially when we deal with the data and transform this data, especially time domain to the frequency domain. So algorithm which do this perform mathematical transforms from time domain to the period or frequency domain. So this is the condition before we do the Fourier analysis. And I think most of you are quite familiar with the topic of Fourier series and Fourier analysis. So for a given frequency nu, where nu is 1 over period in case of astronomy mostly, the Fourier transform is given by this equation. I think it's quite familiar for you. And remember that there exists an Euler formula in which the expansion term can be represented in cos x plus I sine x. In most of cases in astronomy, the imaginary term can be avoided or can be ignored, and mostly we deal with cosine x. And of course, making just a transformation is not enough. We have to find the amplitude, because basically we try to find what's so-called the resonance between the frequency, trial frequency with the true frequency. So when we speak about the physical feeling about this, it's quite natural. In wave theory, we learn about interference, phase difference, wavefront, and resonance. Resonance is one of the phenomena that inspire Fourier transform and time series analysis. But then, when we talk about the basic, remember that your data plays the limits on 2 aspects. First, the range, time window. My talk will be up to 11:30, but I have plenty of slides. So that means I have a short period resolution so that I can convey all the slides to you. This is a very good analogy. So there are 2 parameters, very important, the resolution and the range. Sometimes people call the window. And if you remember Fourier transform of each function, it gives you a very good idea about how a box can be transformed into a sinc function, how a comp function can be transformed into the delta function. That's a very basic of Fourier transform that you have to master first before you understand the time series analysis. So if you have short span of data, both the period and resolution and range will be lower than if you have the longer span. That's the rule of thumb, I think. The basis, of course, you have longer time, longer span, but longer span of observation is expensive, because first, for the time sharing telescope, you need to apply, and you have to compete strongly with the other astronomers who like to use the telescope time for that. If you are not in a very privileged place, you are in an underprivileged place, many of your observing span is hampered by presence of cloud, bad weather, or failure of instrument and everything. So this actually play a role in limiting the resolution and range that we like to achieve when making observation. And yes, the next is period, range, and sampling. So suppose you have a data set spanning 5,000 days with a sampling rate of 10 data per day. Okay? What are the formal optional values of? First, you have a maximum period is 5,000 days. Well, 2,500 is maybe better for this, and the minimum is 0.2 days. It's a sort of limitation set by the instrument itself. Or, for example, you may be able only to observe in optical. You only be able to observe in the nighttime because of the presence of the sun. That actually limit the shortest period. Then you have a dp p square over 5,000 that then will be used to define the frequency here, the range, the interval of the frequency in which you like to sample, the period range that you like to investigate here. So we have n divided by large n times multiplied by delta, where n is equal to n, large n. Large n is the number of data from large number of large n divided by 2 minus 2 to plus around the zero frequency that we like to investigate. So this is the effect of time span on the Fourier transform. So if you have the t span 2670, then you have what's called a low resolution spectra on this power spectra. It's quite well, as you may see here, it's not as detailed as this one. So this will give you that for the RS confined type star with the period of 328.53 days, surely you may have a more detailed power spectra if you make a span of, say, 35,623 days. But of course, it's excessively long for any particular type of observational research nowadays, because nowadays we are very much dictated by a short span of time, but giving a big yield. Then this comes to another scope of discussion. Remember, if we think about the telescope in the world, there are many big telescopes, but there are many small size and intermediate size telescopes. So if we think about utilizing small type telescope or intermediate size of telescope in which you are familiar with, dedicated for this kind of observation, actually you are in a good position to make an observation lasting for a long time span in order to secure a better coverage of variability, and then to make a more a deep analysis, a time series analysis for one particular star that you like to observe. So when I was as old as you, mostly, so the characteristic of astronomical observation mostly well dominated by that kind of observation. We try to to observe and to monitor the light of a particular object, but this of course will not be a very good option when you do survey observation, in which you like to grab a big number of objects that you like to observe, perform statistical, and try to get as quick as possible characteristic of the population under your study. So it's quite depend on how you choose. So from what I have already explained, that brings us to what's so-called the Nyquist-Shannon sampling theorem. Okay, so basically astrophysical process is a continuous one. Light curve, radial velocity, temperature, pressure, humidity at a location, it's a continuous process. But the data as sample can only be acquired in discrete way, because you have a sampling rate. And this sampling rate may be dictated by exposure time, cadence time, okay, limitation, or even it is limited by observing window, in which you can only observe in the nighttime in case of optical and infrared. But maybe in radio, you can make the 24 hours observation continuously, for example. And sampling rate determine range of frequency that can be analyzed. And remember, there are many phenomena such as aliasing. The two periods can fit the data. So in that case, which one is the true period that we have to decide? That we come to what's so-called the theory of aliasing. Later on, I will discuss about this. If a function xt contains no frequency higher than b hertz, hertz is a unit of frequency, it is completely determined by giving its ordinate a series of points spaced at 1/2b seconds apart, because 1/b becomes a second. This is a very famous Nyquist theorem. So from practical point of view, in the handout, I will give you this how to actually implement this Nyquist criteria in your data. So in other words, Nyquist theorem states that a periodic signal must be sampled at more than twice the highest frequency component of the signal, because the shortest the time span, if you inverse this, then it becomes the longest in frequency because of the inverse relation. So in that case, we have a perfect reconstruction of the signal. So what happens if you make a longer frequency? Actually, you repeat the same fundamental one again and again. So this maybe answer the question from one of you asking about how if we make a long periodogram in terms of the frequency, you may repeat the same appearance of the periodogram, and then it confuses you because sometimes it's difficult for you to determine which one is the best frequency or period representing the phenomena that I'm observing. So understanding the Nyquist interval, Nyquist frequency, Nyquist-Shannon sampling theorem is very fundamental in performing frequency domain analysis in time series. So basically, in the observation, you have a continuous one. This is illustrated here. And then depends on how you decide the time exposure, how you decide the observing window, whether from here to here or from here to here. And information and resolution determines how short the time from one exposure to the other exposure. And then basically you sample this continuous process into this discrete process. Then we have two issues here. First is the resolution and the sample and alias. In case of resolution, think about you have a short period, but you sample your data. For example, your period actually is half hour, but then you sample the data, okay, every 2 hours. Of course, you lose the variation within half hour of that. So that means this transform into this. This is your window transform into this.
I'm sorry, Pak Hakim.
Yes.
We cannot see your pointers.
Oh, okay. Yeah, laser pointer. Yes, okay. Yeah, you transform this phenomena into this. This is the actual one into this, but you observe using the window defined by this, which is longer than this. Then once it is multiplied by this, you lose these spikes here, which contains very important. This is because of poor resolution that you make an observation there. But then if you shorten the resolution, then you lose the window because the window is getting the windows is getting. So sometimes you have to make a compromise between resolution and windows. And then if you lose the window, it comes to another problem, the sample, because you may come to a spurious frequency or spurious period introduced by sampling of this. So that's why making a time series analysis is not just a question about post-observation, but it is also addressing the pre-observation strategy for this. Okay. So what happens if you suffer from Nyquist frequency? You have so many peaks here. Okay. Our intuition brings us to a conclusion that the highest peak is the best. But remember what I have already shared to you, that the best period in my analysis of INCOM, the central star of LT5, that comes not from the highest peak in the periodogram, but the second highest peak of the periodogram. Why? Because I performed spurious period test. And luckily, I found a very old paper published in 1948 by Tanner, telling us a very straightforward way to test whether this is an alias of this. This is an alias of this. This is an alias of this. Or maybe this is itself an alias of this. So Fourier transform can recover period much shorter than the sampling period, but transform will suffer from what's so-called the aliasing. So once again, compromising between resolution and window is very span is very important in order to get the most optimized. And this comes actually before the observation. Once again, you have to be keen enough to look not only into the data, but how the data is obtained. It's very important. Okay? Yeah. So let's jump into the method itself. The Fourier algorithm is firstly come as a FFT. Then when it is computerized, it transformed into the it changed into the it is modified into discrete Fourier transform, the classical algorithm. While fast Fourier transform is very good for lots of evenly spaced data, most of the case in astronomy is very unlikely. We mostly have unevenly spaced data. So therefore, astronomer devise what's so-called the date compensated DFT and for unevenly sampled data with lots of gap. This is especially modified from FFT. The ones in the hands-on actually addressing on this date compensated discrete Fourier transform. And I hope you already have their hands-on with you. And Rom and Scargill introduced a very famous periodogram, similar to the FT, but a very strong emphasis on the power spectra analysis with its statistical properties. Remember, once you have the period finding, in the notion in astronomical observation, you have to also estimate the error. So making the error, the statistical analysis of the true period is also quite cumbersome because you have to, of course, go through the analytical process, try to identify the first source of error, propagate this, and finally you get the error estimation, the most perfect error estimation in the period finding that you found. And later on, astronomer will try to falsify or clarify your period by using O-C analysis and so on, once the data is already collected there. So the application of Fourier transform has been expanded and has been modified from time to time. It can cope with multi-periodic data. People in asteroseismology and helioseismology, basically they still use Fourier transform, but then they modify this, and then that's suitable to handle multi-periodic data. And for spectral measurement, of course, to filter the spectral measurement from red noise, people use the Fourier transform. And getting the information that's very important, which is the amplitude and period of evolution, is also using the Fourier transform. And yes, a light curve shape can be estimated via Fourier harmonics, because basically Fourier transform is based on the combination, linear combination of geometric function like sine and cosine. So any disturbance on the light curve shape or any variation shape can be approximate with the Fourier transform with harmonics. This is the famous formula. I'm not going to explain each of the formula here, but this is the paper that I read long time ago and still read by many astronomers until now. Scargill, a seminal paper by him, and later on by Lom. So time to time it appeared as Scargill and Lom method. It was published in Astrophysical Journal in 1982, and I was lucky to be a master student in 1987. So that's why 5 years after he published, I read very thoroughly his paper. And basically, we try to construct this. This is a power spectra against the frequency omega here, where the t is observing time there, and xt is the observable, the one that you observe. It can be magnitude, radial velocity, polarization degree, etc. And then you construct with this. Then once you do that, keeping in mind, you have to be very careful in defining the range of frequency, the step of frequency, trial frequency that you like to use, and finally inspecting the peak here. So this is a very nice case, a very peaceful case, because it comes with one single peak here very easily. And this use the date compensated discrete Fourier transform. The prescription of this already written in the hands-on. And the case of DT Virginis, I gave it to you for your exercise in this afternoon, hopefully. But of course, you have a liberty. You can take liberty to perform this in any computer tools that you like to use. You can use Excel or R. I prefer not to use Excel for doing this, because I have, I myself, I don't like so much Excel. But many of you might use Excel. That's okay for me. That's okay for you as well. So this is actually what is the shape of AW per se. This is a pulsating star with not so sinusoidal shape here. So that's why they use additional terms here to represent the light curve of this AW per se. But with the fundamental period that comes from the Fourier analysis of the light curve of this variable star. So that's all about the Fourier transform. You have to pay attention on the resolution, on the windows, and on the selection or the span of frequency and the interval of the frequency, which is not explicitly written here. What is the best interval of frequency to be used? It's quite depend on your computer. Of course, it's quite depend on the CPU time. It's not an issue anymore, unlike in my case, when I perform a periodogram analysis using an old computer, an ECPC. I remember on that time, it took 15 minutes to finish power spectra from 0.1 day to 10 days with an interval of 0.1 days. But think about the very natural limitation in astronomical observation. Astronomical observation is usually for optical, is at least limited by half sidereal day, because we only can observe. And if you take into account the twilight, basically you can observe only up to 9 hours per night. So that can define the windows, the observing window. That then will give you the idea about the observing span that you can set on the time series analysis. So when Fourier transform overwhelmed astronomical analysis for more than 2 or 3 decades, Then in 1980s, I guess, people come to what's so-called independent from any Fourier analysis. It is not because of Fourier analysis is bad, according to them, but a Fourier analysis is solely based on definitely long cosine wave, one particular time series. What about objects that show period variation as a function of time? This may happen in many cases in astronomy. For example, interacting binary stars. In interacting binary stars, for example, the period constantly changes because of the mass transfer. So how can people study the variation of the power spectra, variation of the period against the time? Fourier transform cannot do that unless you go through a very tedious process like pre-whitening and try to collect the data. But how can from one single observation, okay, or very not single, sorry, but how many is from a small number of observations spanning over time with many blocks here, so we can detect any period change quickly. Then people were introduced to what's so-called the wavelet analysis, and this is a very excellent tool to analyze the changing period. The only thing that not really very much implementable during my time is because you have to analyze the power spectra as an image, as I show you here. This is an image actually. It has a three-dimensional. First is the time, and this is the trial period, and this is the amplitude of the power spectra that you have to show. You need a very good visualization technique to show the wavelet analysis. This is not the issue anymore now, but during my time it was an issue because most of the computer has a limitation for graphical display in that time, especially imaging display. But this is powerful. So while Fourier analysis is based on indefinitely long cosine wave of a specific frequency, this shows you here, wavelet analysis is basically based on a short duration wavelet or kernel of a specific center of frequency. Imagine that you have data against time, and then you apply this kernel, multiply this into that. Okay, and you use another period because this wavelet itself is characterized by two parameters: the time itself and the frequency that introduce the amplitude. And then for any kernel with the different time and amplitude that you introduce, you multiply this with the data. This will give you that wavegram, yeah, wavelet gram that I showed you before. So of course, wavelet analysis is also popular, but it has its own application. Mostly, this is used for long period variable star that changing its period itself, including Myra type variable with stable pulsation, and many mode switching like in Zeta Orij. Yeah. Zeta Orij is one of very enigmatic star that's showing many mode switching, the frequency switching of the pulsation of this star, or cataclysmic variable that can have transient period like superhumps. So wavelet analysis is very ideal for this case. And moreover, wavelet analysis of observed data is good for long data strings, and particularly with no short or no gaps in that. You may see this as a of course limitation of wavelet, but basically wavelet is very tough. Wavelet analysis is quite adaptive and robust against any kind of data. But you have to be very careful in selecting the windows with this one. You must be very critical in defining the amplitude and the width of this frequency because it's a Shannon function actually. And Shannon function is characterized by the width in that time. So be careful in selecting the window width. The smaller the window, the worse the period resolution. But the larger the window, the worse the time resolution. So period resolution and time resolution are two things that cannot be go hands in hands in wavelet analysis, unlike the Fourier transform. So this is what's so called, when you analyze this, you have this as the time of your data, and this is the trial period. It can be as fine as this one, or it can be as coarse as this one. If you have a smaller window, less period resolution, but if you have a large window, you can have a less time resolution. But it's quite up to you to identify which period is the best here. It can be here. It depends on the degree And yes, what is seen here, you need a very good visualization technique in wavelet analysis. Because we are very sensitive in looking at the graph, but not really sensitive in looking at the image. Okay? So how can you find a single best period when you look at the wavelet gram like this? Okay? So it's quite depend on the purpose of using time series analysis. Some time series analysis is very powerful in one aspects, one kind of work, but it can be more suitable if we use another one. So all have the same equal weight in one particular projects or objects that you like to study. So we leave this frequency domain and wavelet analysis, one thing that I introduced to you. And we come to the statistical method of time series. This comes into two categories, the correlation and autocorrelation, and analysis of variance. So in correlation and autocorrelation, which you can find very perfectly written in the book by Fagelson and Babu, how does the star at time t differ from that star at time t plus tau? Yeah. And while in analysis of variance, or what's so-called the ANOVA, what period foldings minimize the variance of the data set? This is more or less looks like the TDM. But in some case, ANOVA use the bin moving average, but in some case, ANOVA can use the whole data. Again, a priori knowledge of this would be very important to see whether you are sure about single period or multi-periodicity that happens in your data. So the way you create the data is very important there. In autocorrelation, for a range of period tau, compare each data point mt to a point mt plus tau. Okay? Basically, you make a correlation between the function and itself, but and try to move it. So the value of correlation function at each tau is a function of average difference between points. If the data is variable in period tau, the autocorrelation has a peak at tau. Once again, it's a multiplication of coincidence similarity will give you a function. This is not called the power spectra, but of course the coincidence, the similarity. Sometimes people call the correlation function, which give you a positive and of course the highest peak that can brings you to a conclusion about this periodicity by trial this tau parameter with the data. This is very much implementable with the high-speed computer now, so that's why for many cosmologists they prefer using these two methods rather than Fourier transform, which is quite extensive. If you like to make an in-depth study of one particular object, maybe Fourier transform or wavelet is a good choice. But if you make a large survey and you like to make a very quick look analysis on the variability and find the analyzability, in many surveys, people use the correlation in this case. So autocorrelation application is excellent for stars with amplitude variation and transient period, or strictly periodic stars, but not so good for multi-periodic stars. So that's why this is usually a good tools of choice by those who make a survey work for that. Remember, there are many variable stars that found by Kepler, by Ogle, for example, survey. They are based mostly on this as first, and then followed up by astrophysicists to study in depth by using more suitable tools to investigate further. Yes, this is an example of autocorrelation study of R-Scuti. The first is a correlation parameter, and this is the time difference that they try to this particular light curve. And then they come to this. Of course, we have to neglect this because this is, of course, the window, mostly representing the window of the data is given here. But this is the first peak that appears here that actually ensure astronomer to find that this R-Scuti has a period of pulsation about 141 days. So one thing that I don't actually touch upon is how to make an error assessment of this period. I think time is quite limited for me to go into that topic, but that thing you can, well, of course, learn more in depth in many papers that I actually give in a file that I share to you in the Google Drive, so you can download and try to look in deeper. If you are interested in studying how uncertainty is analyzed for one particular period finding in time series analysis. Many time series analysis is mostly devoted in period finding, but not making a very deep investigation on how the error of the period can be formalized. And it turns out to be quite case by case in this case. And remember, it has a very strong dependency also in the observation. So that's why you have to propagate this from the beginning. You cannot just formulate the error of period based on the time series analysis. So you have to bring all this error from the observation, the instrument limitation, and propagate this to come to the conclusion about the uncertainty in the period. Okay, so yeah. Okay, before I go to the origin of variabilities in astronomy, because this is going to the last part of my talk, are there any questions up to here?
If you have question, please raise your hand.
Maybe you can also share your experience in using some time series analysis, because I know that time series tools so many, and the one that I discussed maybe it's quite limited compared to a jungle or a number of time series that exist in the literature. And I found that interestingly, most astronomers doing survey, they are very much yes, Arifin, I think you like to ask question. Arifin, please.
Yep. Thank you for the opportunity. Actually, I'm interested in Nyquist problem because, as we know, astronomy, even though we have lots of data, there will always problem in sampling. Yeah. So is there a way to mitigate that, whether we know we are doing the right samples from the physics, astrophysics side? Or
yeah,
we always have to update. In the end, we just have to update because of the data resolution. Thank you.
Yeah, the main drive is the data resolution, Arifin. So that's there is no particular physical. It comes from the theorem in signal processing actually. So think about this. If you have a star observed at your observatory with CCD camera, okay, then because of telescope arrangement, okay, then this image of stars will fall into 3 pixels in your CCD. Okay? Then it creates a circle image. In one set, in another arrangement of telescope, the star image fall into 1 pixel. If you compare this 3 pixel and 1 pixel, from which observation you can gain more information? It's not coming from the 1 pixel image, but 3 pixel image. Why? Because if you like to represent analytically the profile of an image of the star, you need a Gaussian function. And to construct Gaussian function, you need 3 parameters: the amplitude of Gaussian, the width of Gaussian, and the base of Gaussian. How can you construct a Gaussian if the star image fall into 1 pixel? In that case, you have an undersample situation. And that's very frustrating because only 1 star into 1 pixel, no information we can get from that. That is exactly the same analogy with this frequency. So Nyquist sample actually teach us how to think about critical sampling. That sampling that give us as much as possible meaningful information on that. And there is no solid theory about this, except that Nyquist frequency 1/2 delta B. And what is delta B? How can I get this? In observational world, usually we try to define this as the shortest exposure time of this shortest exposure time, and then you can consider this as the smallest time span between one data to the other data, providing that you have a perfect instrument arrangement. And then 2 times that shortest observing time. And if you take the inverse, that is a Nyquist frequency. And remember, because you have a short time, you have a long frequency for that Nyquist frequency, because 1/, shortest period gives you a long frequency. That is the limit where you can make the trial for the frequency checking or period checking for that. But luckily, if you exceed that, because you are not quite precise in Nyquist frequency, then you may come to the repetition of the same pattern at the length. For example, you have the shortest observing resolution, say 1 sidereal day, because you can only observe in one half sidereal day, right? And then the best is, of course, you have the 1/2 times sidereal day is the Nyquist frequency. And then you have, say, because of you have 1 sidereal day, 1/2 times 1 sidereal day is half hertz, half frequency. And then you make a periodogram analysis from starting from 0 to half frequency, half hertz. And then you get a pattern of power spectra. What happens if you exceed this to 1 day? Then from 0.5 to 1 day, you have exactly the same repetition of that power spectra. That is what good in time series. You immediately see, okay, you immediately see the copy of the previous one to the next block. Then you realize, oh, my Nyquist frequency is not correct. I have to improve this. So that is what's so good in Fourier transform. But you cannot detect this if you use wavelet transform. So Nyquist frequency preventing us from redundantly analyze the time series and prevent us from falling into the trap of aliasing. So you may come to the conclusion to the wrong frequency. So I think you may gain your insight once you have this hands-on from me. So try to do that, and then you can have a feeling on how this Nyquist frequency. Try to, and sometimes if you follow the my suggestion, if you look at my hands-on, try not to follow everything there. So try to improvise, try to think out of the box, try to check. Don't worry, you will not crash your computer. But try to not to follow. My instruction is only a guideline, but of course you can improvise to have to gain your insight on many physical insight when you use a time series analysis. That is more important rather than trying to grab all the recipe in time series. So my strategy is not to learn so many time series tools, but try to get the most suitable one and try to learn in depth the minus and plus of this time series tool. So that is, Arifin, my very broad question answer to your question, but you are actually asking a good point in this time series analysis.
Okay, thank you very much, Dr. Hakim.
Yeah, thank you. Okay, so let's move on because I need some time to explain to you about the hands-on before I finish this session, and the time is running. So there are many origins of variability. I just want to share from astrophysical viewpoints, because I'm a stellar physicist. So mostly I talk about the stellar related variabilities in astronomy. But remember, if you do some survey and cosmology, please keep in mind that this may happen in your image. There are some variability in your image that may be very interesting, not really interesting for you, but interesting for stellar astrophysics. Remember, stellar astrophysicists always take advantage of cosmologies because you make a large survey and you are interested in the universe, in the expanding and large scale structure, while we are interested in the object. It's every object that you take the image for your study. So, but if you look one step further, you may see many variabilities in your image that can be attributed to orbital motion, the spectral variation, light variation. It can be from minutes to 100 years, or stellar rotation, and how to actually observe the stellar rotation. Think about our sun, which has a sunspot. Then we may expect, or we may think that star has a greater spot on the star sunspot, star spot. In case of star spot, the modulation, big modulation of the light curve come from the star spot existence in BY Draconi star. R is Canum Venaticorum or T Tauri star. Sometimes in this star, the spot of the star covering the half hemisphere of the star, unlike the sunspot, which is only part per million of the sun circle. But in case of this star, this may come with a very big size. Or neutron star rotation observed from the radial pulse. Also, stellar pulsation is a very famous topic in stellar physics and subject for many time series of study. Well, we have a very good diagnostic from the HR diagram, because from stellar evolution, we learn about surface instability stripes in HR diagram. So if you make a very simple photometric observation and parallax spectroscopy and you put in the HR diagram, when you position the star and for the star falls into the instability strip, you may suspect that this star is pulsating. Then time series analysis is quite imperative for this kind of stars. And remember, the pulsation of the star is also used by galactic astronomers for one of the distance candle for R Lyrae and other stars. And yeah, quite recently, people are very much interested in asteroseismology, and that inspired by helioseismology study. So this is a great challenge for time series analysis, because still people improving time series analysis to detect as much as possible non-radial mode in oscillation. That is quite another branch, the asteroseismology, but it's heavily rely on time series analysis of a number of data that can be used efficiently in order to detect multi-periodicity in the stars. And remember, I used to involve in one campaign coordinated by Space Telescope Science Institute on the study of NGC 1501. That's a single star planetary nebula which shows non-radial pulsation. So non-radial pulsation is also happen in sub-dwarf stars, which is the central star of planetary nebula. Still, many physics must be formulas to explain astrophysically why such white dwarf star can pulsate in such a non-radial mode. And speaking about magnetic activity, the closest star from us, sunspot, display or exhibit as manifestation of magnetic fields from interior emerge to surface, in which we learn about reconnection, solar flare at radio and X-ray, gamma ray, and erratic variation with time scale from milliseconds to minute. Even our sun deserves time series analysis up to now in order to find many helioseismological parameter, how the wave propagate in the interior of the sun, to study that. And we still have a large sample of flare stars yet to be observed, especially DME flare stars, RS Canpen, and T Tauri stars. And this may give us a very good insight on how interstellar matter can be enriched by large flare from the stars instead of mass transfer convention from binary. We still have a wide percentage of single star that show flare star. And this flare star, this large flare star, people think about it has a good contribution on the enrichment of interstellar matter through the flare process. Accretion disk is very fancy topic. Two stars orbiting closely each other, and mass transfer from donor to accretion disk around the receptor. And the accretion disk itself is a variable object. It has a strong X-ray and ultraviolet emission, and varying with time scale from milliseconds to year. So this is also a subject of time series analysis. So quite stochastic one, but quite deterministic one is the stellar explosion, because most of the data collected by astronomer related to stellar explosion mostly come after the explosion, or from the explosion to when it's fading. But it is hard to predict when the star is going to explode. It's quite a stochastic process. Then catching this to the tip is very important for astronomer to understand how the star actually eject heavy materials from the inner part during the explosion process. And we have to think also about cleaning our data from many variability resource because of our observation, like seeing scintillation, parallax, occultation, and gravity wave. So a bit remark on the period finding. Motivation in time series data analysis is to find cyclic seasonal pattern and to get the period. This then will be used for predicting and forecasting. It's not stopped after you finding the period, but you predict this, and it will be confirmed by the next or yourself if you like to make a longer time span of study. I did observation 30 years ago for LT5, and in the year 2010, maybe one astronomer contacted me telling me that he halfly confirmed my observation. He liked to continue using fiber flat high resolution spectroscopy, and I'm quite happy to learn this communication from my colleague in Ireland, but he's now in Italy using the Padova Observatory, who like to follow up this observation. And second, to find the period, or basically the cycle, several ways have been devised depending on two aspects: equally spaced or inequally spaced data. Later is mostly happen in astronomical world, inequally spaced data. An example of method often used for unequally spaced time series data with cyclic pattern approximating sinusoidal function is the Lom's-Cargill method. While for equally spaced time series, often the conventional FFT is used. So many robotic telescopes, for example, they have a very good time exposure, very regular one. In that case, you may use FFT for this. So in astronomy, although historical, the string length based method such as phase dispersion minimization up to now is still used for non-sinusoidal pattern of observable light curve. Remember, not all light curve representing the sinusoidal change. Some show some disturbance in sinusoidal function. That is where the limitation of Fourier transform may happen. It doesn't mean that Fourier transform cannot do that, but you need more time to analyze using the harmonics in Fourier transform. Phase dispersion minimization offer you the quickest way to extract the period from the non-sinusoidal shape of any variation. Okay, so to summarize what I've been giving you here, many time series analysis methods exist. Choose the method which best suits your data and your analysis goals, and beware of the limits and strength of your data. Well, there are some computer programs for time series analysis, not really extensive. This is just based on my experience. Yes, the AVSO is one of the famous one. It's available at Windows 7 up to Windows 10, but now Linux and Unix user can use that. Period 98 is also somewhat old, but Penn State Astronomy Department keeping the statistical code. If you make a program, you can call the library here and of course port this into your program. I'm a Fortran user, so that's why I mostly use develop program in Fortran in BASIC, but now you can use a very nice book that introduced by yes, Eric. This is a very nice one. You can use, I'm not really familiar with R. I use R with very limited capability, but I'm sure you are younger and much easier for me. So I actually upload one file in which you can read through this. But when I look at this, when I make a survey on periodogram analysis, I try to classify this. Many publications related to the methods. But this method is mostly improvement of the previous method, but always addressing on unevenly spaced data. So many, of course, for example, Scargill is the most famous one, but the one that I'm going to introduce you through the hands-on is based on Scargill, but modified for that compensated one. And this is the list of the method that I already learned, including CLIN, the famous one it's used by radio astronomy, the maximum entropy analysis. I think somewhere in this course is given to you, and maximum entropy analysis has been touched by Eric in the beginning of the lecture. So statistical analysis of periodogram is also important for you to read, because the question is sometimes, if I find the period, what is the uncertainty in this? So not so much paper addressing this, unfortunately. I found only 3, maybe 4 papers, but Chris Kuhn, number 2, has a very good series of papers addressing about the error, yes, in the periodogram, in the period determination. Okay, and of course there are not so many, but some of the paper, of course, addressing a comparison of one and the other methods. I think it's good if you have time to read this. in order to, once you are a good time series practitioner, then you can, but if you just want to pick up one particular, you better try to devote yourself only in one particular here, and also the statistical analysis of the parallelogram. Stating uncertainty is very important in any astronomical research, because you cannot just claim the parameter, but you also have to make an assessment of the error and present the result. So at the end of this lecture, I'm quite optimistic. Time domain astronomy is growing from time to time, along with the telescope size, along with the opportunity of using a telescope. So be optimistic, and time domain is something worth that to be pursued in the future. Thank you very much. Evan, I finish the lecture here.
Thank you, Pak Hakim. Before we move to the explanation about the hands-on session, do you have any question?
Yes. I think people are getting hungry. People are getting hungry. It's getting hot in Indonesia, of course.
Yeah, we have Chandra.
Yeah, I think Chandra and Ibnu. Yes. Up to you, Evan.
Can you hear me?
Yes. Perfect.
Okay.
I can see you as well.
Good. Okay. Good morning, and thank you for the occasion. I have a question about the Nyquist Shannon sampling theorem.
Yeah.
Nyquist theorem states that a periodic signal must be sampled at more than twice highest frequency. So this is the lower limit for resolution. Is that right?
Yeah, that's right. And the highest frequency value.
So is there a higher limit for resolution? I mean, if is there a drawbacks if we choose a very high resolution for sampling?
What I mean is the lowest value means the highest resolution. So Nyquist frequency, the inverse of the lowest value of resolution, means the highest resolution, Chandra. So resolution means what is the interval, the shortest interval you take the data. And accompanying the resolution is the span or window. So you play with these two parameters. When you start your observation, when you finish the observation, that defines the window. What is the shortest time exposure, and what is the interval between one exposure to the other, that defines the resolution. So if you shorten the time resolution, you shorter the interval between one exposure, you achieve the highest resolution. Okay, but remember, in Fourier transform, you have to pay careful attention in these two parameters, your span and your resolution. So 1/2 smallest resolution will give you the Nyquist frequency, the highest frequency trial that you have to achieve, you have to do. So it's not necessary for you to go to longer frequency, higher frequency, because basically you repeat the same power spectra with the previous one. Yeah.
Yes. Okay. That's clear some doubts. Thank you very much for the explanation.
Okay.
Okay. Next we have Ibnu Nurul. Please, Ibnu.
Yeah. Thank you very much for the opportunity. Hello, Pak Hakim.
Hello, Ibnu.
Very nice presentation. I just want to ask about if we want to search a period of the phenomenon, for example, and we just have a noisy signal, and if we do the Fourier transform, the period does not have a clear peak. I mean, because the signal is quite noisy. Do you have a suggestion what statistical technique that I must to use?
Yeah. My suggestion is to you, of course. Well, again, if you just dump noisy data, noisy, I don't agree with the term noisy data, white noise. Then Fourier transform will give you exactly the white noise as well. So mostly we tackle the problem before we plunge the data into the time series analysis. So that is where the step of carefully look of the data is imperative. you have to clean the data somewhat. The process so-called the pre-whitening sometimes before the time series analysis is actually you try to move all this white noise, instrument noise, and get the most essential data that you have to do. So the message is not to just put all the data into that. You have to transform the data. There are many ways in detecting the noise data. First, you can transform, get the histogram of the data, for example. Then if you have a very normal, for example, if you talk about the bias of CCD image, what happens if you take the histogram of the bias? It will give you a very nicely normal distribution. Then you may suspect that is the noise of the data. But if your histogram is somewhat skewed, the data exists in that data. Okay? Data exists in that image, in that series. In that case, you can try as hard as you can to remove all this noise prior to make time series analysis. Because once this noise enter into the time series analysis, then you come up with the result that really confusing you because of the presence. Many people also introduce the filtering technique for that. The best is, of course, to make a Gaussian filtering, low pass filtering, high pass filtering. So it's quite depend on your knowledge about the instrumentation condition, and that has happened mostly in radio. No, I know many people in radio deals with this. Yes, that's in also in infrared. So they use this, of course, making the histogram, try to reject white noise, try to minimize all this noise prior to put this into the time series analysis. The advantage of radio is you can make, of course, the shortest time resolution, because basically, and in radio you have a largest span of observation because you can observe day and night. Unlike optical astronomer, we are only limited by half sidereal day, which is not half day, even less than half day, but you can make observation day and night in radio. So in radio, you have an advantage of the span, but not in the resolution. Resolution is still superior in optic in terms of time as well as. So very good question, but of course, you have to think about how to deal with the data before the time series, and that is the most important one, and give a time series chance to detect good period based on the good input from the data.
Oh, okay.
So
Thank you very
that's
much.
maybe just a suggestion. You know better than me, of course, with the data.
No, no. You know, thank you very much.
Yeah. Okay.
Okay, next we have Alia. Alia, you can ask directly.
Yes, Alia.
Thank you
Alia.
very much, Pak Evan and Pak Hakim for the lecture. I'm sorry I can't open my camera because it will crash my device.
Okay.
I'd like to ask,
Okay.
I'm sorry if it's already explained before, but how do astronomers find the periods in a multi-period system and differentiate each period? Like maybe in a binary system there is a pulsating star. Yeah, how do they find the periods and differentiate them?
Yeah.
Maybe from the spectrum.
That's right.
Spectrum. Thank you
That's
very
right.
much.
Thank you, Dalia. That's a good question. How actually we go through multi-periodicity analysis from the time series? Basically, before it's getting as advanced as now, the simplest way, the most classical way in doing multi-periodicity analysis is first, we make Fourier transform or discrete Fourier transform analysis and get the power spectra by carefully define the Nyquist frequency and the span in order to get the fundamental period for that. And once we have the period, we assume a sinusoidal function with that period. So we fit this sinusoidal function on our data. Okay. Once you have the sinusoidal function with the data, you can get the residual of this light curve or whatever observable. So this residual, you keep it with you, and then you put this residual data into the time series again. Remember, the data that you input the time series is already subtracted from the period. This give you only the residual after you having the after you detect the fundamental period. If there is another period exists, you may have another power spectra that shows you peak. Then you get the second period from there. Then again, you fit the sine curve on your data, you get the residual, and then this residual you put into the time series again in order to detect the other period that may be happening. You do it until you have no period in the power spectra anymore. That is the simplest way in detecting periodicity. So it's a repeating process, using first the whole data and next the residual data and next the residual data. So I did it actually in back 30 years ago, but now using the wavelet, for example, wavelet is a very powerful tool actually to detect multi-periodicity, because wavelet give you the result of the periodogram in 3 dimensions: time, period, and the strength, amplitude. So in that case, you can identify from this wavelet gram many potential periods that can be used. So there are many ways of doing that, but the one that I think may gain your feeling about how to detect is using the Fourier transform and repeat that process for the residual data. So that's my answer, Alia, for your question.
Okay, thank you, Pak Hakim. Next, we have one more. We have Ehsan Mauli.
Yeah, Ehsan Mauli.
Hi.
Nice to meet you again. Yeah.
So my question was that so basically the Nyquist ray sampling theorem states that the highest frequency that you can represent is basically half of the sampling rate.
Yes.
So when the signal that you're observing exceeds that highest frequency set by the Nyquist theorem, you said that aliasing happens. So could you explain how that aliasing happens and if it can be prevented by, say, setting maybe filters or something so that after that frequency, we cut off any signal that comes up?
Yes, yes, alias is happen because we have to, the feeling is why alias happen, because here, this is a good example. Suppose that the period of a binary that you observe variable star is exactly 1 day, okay, one sidereal day, and then you observe with the observing window exactly 1 day. Then when you make a periodogram analysis, you have many peaks: 1, 2, 3, 4, 5 days. So what is the intuition that we have to go into this? We always think that the fundamental one is the true period, but that is not necessarily true, because there may be a variable star with the period exactly 2 days. So this alias happen because we limit the window, and this limit of window is just fall into the period of the star. So what should we do this? Tanner in 1948, he is inspired by the synodical period and sidereal period. And then he tried to relate this rotation period with the period that he under his investigation. So the intuition is when you have this alias, so the lowest frequency appear in the alias is most likely the true period of that. So that's the limitation mostly by nature assembly, not by the technique itself, okay? Because we are observing, and think about if we don't know exactly what is the period beforehand, so we have to guess this. So what can answer this alias? Of course, the making. That's why, for example, when we make a astroseismology of non-radial pulsating star, in order to prevent this alias happen, astronomers from Space Telescope Science Institute, they campaign this. They make a call for observation around the world, so the coverage can be continuously. That's the best way to prevent aliasing.
Right.
Yeah.
So suppose you have a lot of frequencies in the signal, and some of them are below the maximum that can be represented, and some of them are above that. So will the time series frequency pretty much look like this, and then just taper off once the aliasing starts? Because
well,
of the
yes,
high frequency?
basically the fundamental one is the highest peak. basically,
Okay.
next to the window pattern. So that's why you can feel sure that if you get that highest power in the power amplitude, you almost actually come to the most correct period in that case. Yeah.
Thank you.
Good question. I see Hafid is raising
Yes,
his hand.
Hafid, you can ask the question directly.
Okay. Thank you.
Yeah.
Pak Evan and Pak Hakim. Thank you,
Yes,
Pak Hakim,
Hafid.
for the great lecture.
you.
My question is, could you please comment a little about how we detect transient signals such as gravitational wave using time series analysis? Because I think the data with the signal would be less than the noise. So maybe we should do something after the pre-processing, but I don't think I know what should I do. So could you suggest something to make the signal more detectable?
Yeah,
Thank you.
that's a good question, Hafiz. But once again, time series is a field which is not so much sensitive to the signal to noise data. Why? Because time series analysis already take into account the white noise quite well. Unlike, for example, if I compare with the, say, defining the light curve itself, in the SDSS survey, so people try to devise different scale of magnitude, not the Poisson scale, but the Luptonian scale, Luptitude. The reason is because most of the data that they obtain, the signal to noise is terribly low, under 5. Okay? But what happened when they make the variable star survey from the SDSS? Yes, surprisingly, all the period finding does not affected so much by the low quality of the data, provided that you clean all the data using the pre-whitening process from the instrument noise, from the white noise, and then it will leave you on the real signal. Although the signal to noise is very low, it's still worth to be analyzed with time series analysis. So time series analysis does not depend so much on the signal to noise of the data, but quite the nature of variability of the data. So don't worry about that, about this. But of course, you need a certain process to ensure what you input into the time series analysis should represent a very close to the variability, intrinsic variability represented by the data. So not contaminated by noise. That is another thing that you have to take into account, cleaning the data from the noise itself. But no matter how the signal to noise of the data, it still can be analyzed with time series analysis. And many people succeeded in analyzing low signal to noise data with time series analysis.
Okay, thank you for your answer.
So it's 11:10, Evan. So I think,
it's time for you to explain about the hands-on.
yes.
I think.
Okay, so next is I'd like to invite you to go through this slide about hands-on in search and determination of periodicity in astronomical data. This is supposed to be very straightforward, I hope, and I hope you can understand this. Yeah. So this is based on a book. The book, I still took the book here. This is a book, Exercise in Astronomy, which I use very much. I hope you can see. Oh, no, because of the background. Okay, later on. But you can find it here. And the paper by Ferraz Melo, 1981. Yeah. Okay, so the problem that I'm giving here is date compensated discrete Fourier transform, one that I show you. It was developed first by Ferraz Melo, 1981, and has been used to carry out time series analysis in astronomical observational data, which is characterized by irregular measurement time, small variation in measured quantity, small number of observational data. And the number of data, do not surprise, is only 20 that I'm going to give you. 20 points of differential photometry. It's basically a light curve of DT Virginis. So the objective of this hands-on is to find the period of variable star DT Virginis. The spectral type is M1.5. It's a flare star, actually, from differential photometry in filter B with a total number of 20 points. So observations were carried out in 3 months in 1972. So the reference of this observation could be found in this, the ETA survey, and Torres and Ferraz Melo in Astrophysics 1973. So the material that provided to you is data of DT-FIR in filter B, and the observing window is 3 months in 1972. Date is expressed in Julian date, and magnitude difference delta B, the magnitude of the delta FIR against the comparison, the difference. So the data looks like this, not so much. As you see here, you can simply enter this into Excel. And remember, because of this is a JD, I only take the last 2 digits in the integer part. Yeah? But remember, this is part of 2441400. Okay, and this is delta B with 3 digit behind the decimal. And there is a report about the standard deviation of sigma delta B, which is 100 magnitudes. You may think about having this for your error assessment if you like to analyze this later on. So what is the procedure? Create a table consisting of Julian date, relative magnitude, and difference between delta B in each date against the mean value. And try to inspect the date. You can use Excel for inspecting this if you like. And at one, you may see that the spacing between consecutive days is 1 to 24 days, as you can see it from here. For example, the difference between here to here is 24 days. Okay. Oops. Okay. I have to use the pointer for this. And then you try to inspect the difference, because checking this will give you an idea about how to calculate the Nyquist frequency here. So plot delta B against JD. You plot this. Observe the graph. This is a graph. If you look at this. Okay. So carefully look at the relative magnitude. The amplitude of variation is significant. Yes, you see here there's a difference, the amplitude, but no clear period in here. What is the period of this? What is the shape of the light curve? That's the basic question that you have to answer here. So then we define Nyquist frequency as twice minimum spacing between 2 observations. So in the case of DT-FIR, if you inspect the date, so you may see here that the minimum spacing is 1 sidereal day here. The minimum of this is 1 sidereal day. Remember that 1 sidereal day is 0.99, something like that, of the solar day. So the Nyquist frequency would be 1/2 times sidereal day. So if you have 1 sidereal day, 2 times 1 sidereal day means 2, and 1/2 is 0.5 or something like that. So while the Nyquist period is 2 sidereal days, the Nyquist frequency is half Hertz. Okay. So this is some table that you can construct of this. So the algorithm of DC-DFT is full with mathematics, and this is the challenge for you. I will give you time for in the afternoon session, of course, to try to implement this mathematical formula into your code. If you are good in using Python, I suggest you to use Python, or in R, you can use R for this. But this is the whole algorithm that you have to go through this. So start with each trial frequency. Remember, your frequency trial is from 0 to 0.5, 1/2. So what is the step depends on how good the power spectra graph that you like to show. So in this DC-DFT, instead of power spectra, they use spectral correlation. Okay, that is because he argued that spectral correlation is more appropriate term than amplitude of power spectra. Well, if n is number of observation, ti is observation date, xi is equal to 2 pi omega ti, summations done from 1 to n, and then you go through all this equation. Choose the range of frequency to be investigated. Usually, we consider omega equal to 0 to Nyquist frequency, but please avoid omega 0 since it may cause singularity. because some of the calculation may use omega and try to avoid omega. So you can start from omega 0.01 or 0.001 up to 0.5. Okay, it's not a very big span. So in order to create a good periodogram graph, of course, it's up to you to select the interval of the frequency trial there. Choose the step to be used in scanning frequency range. Depends on what is the precision to be achieved. The small step should be avoided. Small step means that number of step is too small, means that you have a very coarse. So maybe the size of the step must be small, means the number of step must be big. Okay? And plot S omega here. So if you do that, you may get the S omega graph in spec of this. Then the highest peak should correspond to the frequency that most representing the periodicity in time series. So up to the sixth step, actually you are constructing the periodogram. And of course you can end it here if you are not interested in investigating the confidence level of the periodogram. But if you are curious about the statistical significance of the period of your finding, you can go through step 7 to 8. Because step 7 to 8 is to ensure that the decided peaks coming from this spectral correlation is statistically significant. Then basically from step 7 to 8, you are doing statistical tests on this. This is devised by Quast, one of the author of this hands-on, in which he formulates this by assuming normal distribution, probability distribution on the peak. As you may see here, there are some transient function here that actually related to the distribution. And then he compute, but just follow this, compute this and this parameter alpha here. And then basically you are constructing the H, statistical significant H, against the omega that is given here. So you end up computing H here. H is the statistical significance. While C here is actually confidence level of result. It's actually a constant. You can calculate this given H and alpha here, and then you can plot the ISO line here that represent the level of confidence. So you can put, for example, C 95%, and then you can compute what is H, and then you can put that line on the H diagram, and then you get the level of confidence. That is actually one very good statistical diagnostic tool to ensure that the peak that we found has a high level of confidence there. So if you finish, you come up to this kind of graph. The first one is resulting from step 1 to 6, okay? And the step below that figure is actually the statistical parameter. This is H. This is the peak that we like to find. This is a very good periodogram, very ideal periodogram that everybody loves to have this. Okay. So unfortunately, in my life, I didn't find this light curve. 32 years ago, I didn't find this beautiful light periodogram like this. But to make you happy, of course, I will give you a step, and hopefully during that in the afternoon time, you can try to develop your code, try to use this, and once you have this code, you can exercise this code with another data in order to get this. But this is a very important fundamental tool, group tool for you to try to make a periodogram analysis. Keep in mind that performance of statistical method generally depends on date distribution. So from the value omega best, for which the S is maximum, if confidence level is high, one get the period, which is, remember, your periodogram x-axis is still frequency. You have to convert into P here. Okay. So once you have the period, you have to check this period against the light curve. And finally, you make a visual inspection of the light curve that you see. That is where astrophysical interpretation comes. Okay? So eventually, you come to this light curve, and then you may make astrophysical interpretation is concerning the variation, the shape of the light curve itself. Okay, try to exercise to go through these steps that hopefully can provide you with a very fundamental tools in making any time series analysis. Later on, you can exercise with the other data, or you can, of course, yes, revise or improve or maybe modify this program for you. I have a Fortran program. Also, I upload this on the Google Drive. If you like, you can download. If you have Fortran compiler and pgplot in your Linux system, you can easily compile my program and reproduce this. So some experiments that I offer to you, once you successfully make this, try to consider exceeding the Nyquist frequency. Try to analyze 0.5 to 1 day, 1 hertz, 1 over day, as a new interval. That is, you work beyond the Nyquist frequency. Compute the S, compare the resulting graph to see what is the shape of the parallelogram compared to from 0 to 0.5. You can confirm that maybe you find exactly the similar because it's an alias actually. Put the constant value for B instead of this value. Suppose that you change this B with 1. So basically you are transforming the observing windows. You are making a parallelogram analysis of your observational windows. Okay? That will give you interesting result. Okay. So at the frequency 0.65, if you go through first process, new peak occurs higher than 0.30 dB. One peak is the alias of the other. And try to draw a conclusion from this experiment. Further reading, if you are interested in my story in the morning, you can read at this paper to find how fun to write a paper based on this time series analysis. Thank you very much. Good luck for the work. Thank you, Evan. I give it back to you.
Okay, thank you, Pak Hakim. For the hands-on session, do you have any question for the pointers?
Yes,
okay, Esan Mauli.
Hi again.
Yes.
I was just asking, is there any way to do all of these steps using a Python package, say NumPy or SciPy or maybe AstroPy?
Any kind,
all this
any kind.
data.
Any kind
So this algorithm of data specific Fourier transform is available there, right?
Yes, yes, that's right. But even though you just follow all the summation and everything, try to create with Python, it's also okay for you. So you don't have to consult any library with Fourier transform because all the formula is, I think, yes, it's clear there. So just try to figure out how to make a summation with that. So you can use the Fourier, but you don't have to use that. Also, it will do for you.
Yes. And I couldn't understand what the phase was. I mean, why are we calculating the phase? I couldn't understand what exactly what the physical meaning of the phase is.
Phase is a representative diagram for representing. It's a diagram for representing any cyclic phenomena. Imagine that if your star is cycling like this, in one phase he will be like this, and once he come back from that phase. So if you extend the phase from 0 to 1 and to 2, so the part of 1 to 2 in axis will exactly the same with 0 to 1. So you don't have to stretch this. You can make the same x-axis from 0 to 1, and all the data will be folded into that. So phase diagram is a very important graph representing any cyclic phenomenon. So, and that's very common.
Basically, we are representing the shape of the signal.
Yes, that's right, the shape. So any deviation of the shape means that there is an asymmetry in the repeating process in the cycle. Yeah,
okay, thank you.
Okay, is there any more question? No?